So what I want to address in this talk is some kind of, the status of current models and current theory for planets and exoplanets, and also some kind of limitation, uncertainties, and the future as well of the models. And in particular, I think what is important is a kind of important fact for the models and the theory, which is the huge diversity that missions like CoRoT and Kepler have revealed to the world. And this is the diversity of bulk compositions according to observed mass-radius relationship. And when you look at this diagram, which shows the radius as a function of mass in Jupiter mass, and you have models with different compositions, you can indeed see that you have a huge diversity of possible radius for a given mass, indicating somehow that you have a high diversity of possible composition. And interestingly enough, in the realm of rocky planets, it seems that we do have as well this type of diversity in composition, as revealed by, well, our solar system planets and satellites, but also revealed by Kepler discovery of super-Earth planets, where you can see here, so you have models, for example, for typical terrestrial composition, where of course the Earth fit well, this curve, but you have also models, for example, with 50% of water, and you can see that Kepler 11, for example, of Kepler 20c, actually have apparently composition which has nothing to do with either terrestrial planets or a kind of water planet with 50% of water. So now the idea is, are the models, is the theory ready to address this kind of diversity and to interpret mass-radius relationship, for example, which are delivered by high accuracy transit missions? But first of all, I think if we want to talk about models of exoplanets, we cannot avoid talking about models of our own planetary system. And all the theory that we are using now to model exoplanets is actually based on our knowledge of our own solar system planets. But here maybe for people who are not too, I would say, familiar with making models for exoplanets, I just want to briefly present what are the building blocks of exoplanet modeling. So first of all, you have here a planet, and what you need first are atmosphere models, I say 1D atmosphere models, static, and whether irradiated or non-irradiated. Usually they can be used for exoplanets or for brown dwarfs, and they are very important because they're used for boundary conditions for the interior, and therefore they rule somehow the cooling of your planet and the contraction of your planet. Then you need atmospheric dynamics, because we know that hot Jupiters, for example, or planets which are very close in to the parent star are highly irradiated, and there is a lot of dynamical processes going on there which can affect not only the spectroscopic signature, but eventually may affect the structure of your planet as well. Then, if you go a bit deeper, you have a hydrogen-helium envelope eventually enriched in heavy material. This means that you need equation of states for hydrogen, helium, and for heavy material as well. And this equation of state, those equations of state are very complicated because the gas in a planet is certainly not an ideal gas, and you have also very complex processes going on there. You need, of course, evolutionary models when you start to have a hydrogen or a gaseous envelope, because this is very compressible material, and therefore it can contract and can cool down during billion of years. And finally, you may have to include tidal processes for those planets which are close to their star. Then, if you continue going inside, for example, for Jupiter-like planets, you have certainly a rocky or an icy core, which means that you need an equation of state describing the property of this material, which can be either what we call ices, water, methane, ammonia, silicates, iron eventually. And if you are talking, so you can use the same equation of state whether you talk of giant planets or whether you talk of Earth-like, of super-Earth planets. The only thing for terrestrial planets is that you may need to include some more dynamical processes such as plate tectonics, volcanism, or melting. But here in my talk, I'm going more to focus on giant planets. And what we know from our own giant planet, in particular Jupiter and Saturn, is that because of missions like Pioneer and Galileo, Cassini, we know, for example, that their atmosphere is enriched in heavy material, And for example, for Jupiter, because of in situ missions, those missions have been able to measure abundances of those heavy material which are typically enriched by a factor 2 to 4 compared to solar. We also know that the abundance of helium in Jupiter's atmosphere is depleted. For Saturn, it seems also that there is the same type of trend of depletion of helium in the abundance in the atmosphere, as well as enrichment of carbon and of nitrogen. And this is somehow compatible, this metal enrichment is compatible with our understanding of planet formation in what I call a dirty or dusty disk, where your object is accreting all these type of condensates in your disk. For example, the core accretion model would predict this type of enrichment. So now, standard picture for modeling our giant planets is usually based on very common assumptions, which is, for example, what we call the 3-layer picture, and many, many models have been built on this type of picture. So the idea is that you have layer 1, which is here, and which is the outer molecular hydrogen envelope with some depleted helium because of the observations of Jupiter and Saturn, and also some kind of amount of heavy material. Then you have a layer 2, which is the inner envelope with metallic or fully ionized hydrogen, and also with some helium and another composition of metals. And finally, you have the layer 3, which is a central core, which may be icy or rocky. The idea of differentiating this layer 1 and layer 2 is based actually on 2 possible physical processes which may happen. The first one is possibility of a phase transition between molecular hydrogen and metallic molecular hydrogen H2 and metallic hydrogen H, fully ionized hydrogen. And therefore, this would be a first-order transition, which means discontinuity in entropy and in density, and therefore you would have a sharp boundary between layer 1 and layer 2. The other idea also is that helium may actually, you may have a phase separation between hydrogen and helium, with helium making some kind of rain or droplets. And you will have also a discontinuity in composition between this layer 1 and 2. So this is basically this idea of having those 3 models, or at least having those 2 separate, layer 1 and 2. And the other important assumption which is made in any kind of planet or exoplanet model is that actually the interior, the gaseous interior, the plasma interior is fully convective, and the convection is fully adiabatic. Here, what I want to point out is that this existence or possible existence of layer 1 and 2 actually depends on those processes I've mentioned. And nowadays, there are huge efforts which are made to calculate ab initio equation of state from first principle, and which may test this idea of a plasma phase transition, and also this idea of a phase separation between hydrogen and helium. And therefore, a better understanding of the structure of Jupiter actually depends on a better understanding of the plasma properties and on those ab initio calculations of equation of state, which I think is very interesting to see the feedback of equation of state calculation. So now, when we look at modern adiabatic models, so fully adiabatic models of Jupiter and Saturn, for example, which are based on improved equation of state, based on ab initio equation of state, and on either 2 or 3 layer model, we see that actually there is still a kind of degeneracy or possible solutions if you want, for example, to reproduce observational constraints such as the gravitational moments of Jupiter and Saturn. And I would not come into the details here. You have the mass of the core. Here you have the mass of the heavy element in the envelope. Red is Jupiter, blue is Saturn. But you can see there are a lot of possible solutions which still can reproduce our observational constraint. And actually, one of the main issue or one of the main reasons for this degeneracy and different solutions is whether you use a 2 or 3 layer model. But what is also the important information is that for sure, Jupiter and Saturn have a global enhancement of heavy material, which is much more important than the solar composition, with typically a factor, an enrichment and a metallicity, which is a factor 3 to 8 compared to solar for Jupiter, and about a factor 12 to 21 compared to solar abundances. And I think this is important because it means that exoplanets certainly also are all enriched somehow in heavy material. Now, the other interesting idea, which is actually coming back, this was an old idea of Stevenson and Salpeter in the late 70s is whether indeed convection is fully adiabatic and whether the interior of our giant planet is actually homogeneous. And this idea, we somehow resume it a few years ago with Gilles Chabrier to try to explain inflated hot Jupiters. So the idea here is very basic. I will not come into the detail, but the idea is that if you have a molecular weight gradient, actually you are going to inhibit somehow your transport of energy by convection. And this is actually the idea of what stellar physicists very well known with the presence of molecular weight gradients which can inhibit even the convection, and where you apply for convective instability instead of the Schwarzschild criterion, you apply the Ledoux criterion. So basically what happens is that if you have in a region two substances which diffuse like heat and chemical composition, then actually you may form, this is called a double diffusive convection. It's also called layered convection. It's also called semi-convection. It's all kind of the same process. And what is important is that we can find layer formation, for example, in oceans where you have heat diffusion and you have salt diffusion. And you can also find this formation of layers in laboratory experiments. More interesting is that recently with 3D numerical simulations done by Rosenblum, Mirou, and Pascal Garot and those people, they find also the formation of layers in an environment where you have molecular weight gradients, and they can find that in an environment of low prime number, which would be more characteristic of planetary environments. And the basic effect of this layered convection would just be to inhibit the transport of heat from the very central regions of the planet to the surface. That's the main idea, and therefore it will just slow down the cooling and the contraction of your planet. And after billion years of evolution, the planet would have a larger radius. So the origin of this molecular weight gradient is very speculative. The first idea is that it could come actually from the formation process because you accrete a lot of dirty stuff. And therefore, in your hydrogen-helium envelope, when you accrete the gas as well, you will have this type of molecular weight gradients. The point and the big question is whether you can maintain this gradient during a few giga-years. This is, I'm not sure I can believe that, but what is interesting is that if this process happens during the formation, then your molecular weight gradient could still survive at very young ages for your planet. And therefore, because the flux will be inhibited and will not be transported, those planets which would have layered convection would be much fainter than fully adiabatic planets. And this is actually exactly the type of targets that GPI and SPHERE could reach and eventually test this hypothesis. The other idea would be eventually core erosion, and recent molecular dynamics simulations, so ab initio calculations, have indeed suggested that stuff like water, material like water, or magnesium oxide could actually be soluble in hydrogen, which means that if you had a core and if you have an envelope of hydrogen above the core, then actually your core could start to dissolve, and therefore you may have a gradient which could rise eventually and provoke this kind of double diffusive convection. So these are just ideas for the moment. It's very speculative, but well, they are on the way, theoretical models to try to prove these ideas. Most interestingly is that recently Jérémy Lecomte and Gilles Chabrier have applied this idea of double diffusive convection to Jupiter and Saturn, and they have shown that actually non-standard inhomogeneous model of Jupiter and Saturn could reproduce all the observational constraints and above all the gravitational moments. So actually you could also show that you can have those type of inhomogeneous model for Jupiter and Saturn. The first thing which is important is that they actually find that the metal enrichment in this case has to be much greater for Jupiter and Saturn compared to what is predicted by fully adiabatic models. The other interesting thing is that because layered convection somehow prevents the luminosity or the flux, the thermal heat to go out from your planet to escape, then the luminosity of Saturn at its age with double diffusive convection model is higher than fully adiabatic model. And you could solve a big puzzle in Saturn's life, which is that actually the luminosity of Saturn is much higher than what current standard fully adiabatic models can predict. So that's a very interesting idea. And maybe the takeaway message is that inhomogeneous models of Jupiter and Saturn would predict, if you want to reproduce the mass and the radius of an object, would predict actually a much higher abundance of heavy material. And this is important in the perspective of transiting planets where we have only the mass and the radius, and whether you assume that you have a fully convective object or an adiabatic object, remember that you will have actually a totally different estimate of the bulk composition. So this is why this is an important process to take into account. Last thing regarding our planetary system is that actually the future looks very good, because we will have very soon Juno and Cassini, who are going to improve the measurement of gravitational moments, and this is going to improve drastically the density distribution, the constraint on density distribution. And what is very interesting is that now also improved models which take into account actually the obliqueness of planets are being developed beyond the standard expansion around spherical geometry which has been used up to now. And those are, for example, models that my colleagues in the Applied Math department in Exeter are developing. So having this in mind, let us go now to exoplanets. And first of all, because of the constraint are not so high, the exoplanet models are still not using really ab initio equation of states which have been calculated. Most of exoplanet models actually take into account, I would say, quite old equation of state which are based on laboratory government calculations from ANEOS and CSAMI, and those are still very uncertain. There is another assumption which is made to model those interior of planets, is that usually, because it's much easier and we have no real constraints, we assume that all heavy material is in the core, and then you have some abundances of heavy material in the hydrogen and helium envelope. The big question is whether this is actually equivalent. So if you put all heavy material in the core, or you distribute it everywhere in your planet, is this the same? And actually, we have addressed these questions with my collaborator, Chabry and Baumann, a few years ago. And we have shown that if you take a Neptune mass planet, 20 Earth mass, with an enrichment of 50% of heavy material, and you distribute all the material in the core, here the blue curve, it shows the radius as a function of time. And here, if you distribute your material everywhere in your planet, you can get up to 30% effect on the radius. Even more worrying is that if you actually do the same exercise, but instead of using the ANEOS equation, you use the CSAMI equations, then you get also a huge difference. And actually, this difference is due to some kind of different entropy calculations between ANEOS and CSAMI, and also different entropy behavior of metals, whether you put them in the core or in the envelope. And entropy and derivatives of entropy is crucial, because this is actually what drives the evolution. As you know, luminosity of a planet or a star is driven by the contraction or by the loss of entropy, which is due to contraction and loss of heat. But hopefully, the reduction of those big uncertainty will come with those new ab initio equation of state. I would like here to point a very interesting case, the CoRoT planet, which has been discovered 2 years ago. And this is a 4 Jupiter mass. And in order to explain its very low radius, you would need something like 800 Earth mass of heavy material. And this is typically the amount you would have in the disk. So forget it. It's impossible. Well, some crazy people may find out some model. Doug Lynn may find a model to form it. But this is crazy, forget it. What is interesting is that actually, if you, instead of putting your 800 or all your heavy material in the core, but you distribute it everywhere, instead of 800, you may need only 500 Earth mass of heavy material. Well, this is still quite a lot. Nevertheless, so what's the problem with this planet? Is the radius wrong? Possibility. Or is the heavy material distributed all over the planet, but still 500 Earth mass means that almost all the heavy material in the disk goes in just one planet? Difficult. The other idea is that actually there is problem of equation of state that we have used here to do those models, and hopefully ab initio equation of state could improve that. And this shows that those systems, which sometimes have been a bit forgotten, which means those very enriched or very small radius planets, are very interesting because they could offer a kind of benchmark test for equation of states. So this is why we are looking for those type of objects as well, because they are very interesting. So now let's go to the last part of my talk, which is the problem of inflated planets. We know that now when you look at the radius of a planet, there is a large fraction of those hot Jupiters which are actually inflated, and up to 40 to 50% of what standard models could predict. So is there any kind of missing planetary physics in the interior models? That may be possible. What is now clear is that there is an observational trend that this correlation of the radius anomaly is linked with the stellar flux. The higher the stellar flux, the higher the irradiation, the larger the radius of the planet, which means that if you want to explain this type of observations, then you need a process, a mechanism, which is actually driven by the stellar flux. So I think there is now two favored mechanisms for that, which is pure atmospheric circulation, which has been suggested already, I would say, a long time ago by Schumann and Tristan Guillot, and which would be the idea that your strong winds due to irradiation could induce somehow a downward flux of kinetic energy and heating the deeper layers. This is still under study, and it still has not been really proven. The other idea is based on ohmic dissipation, which means that on the top of dynamical process, you need magnetic field, and your magnetic field will somehow create electric current, which may actually dissipate deep in the interior and also add some kind of extra energy. The point is that now we have no answer, and if you want really to study those mechanisms, what you need to do actually is you need to do global circulation models. This is the only way to really try to model this type of process and understand whether they can explain inflation of radius of planets. So global circulation model is just a hydrodynamical study of atmospheric circulation, which can be induced by strong irradiation. And there is now a lot of efforts by different groups in the world, in the States and in Europe, and trying to couple 3D hydrodynamics, radiative transfer, and eventually some MHD effects like a magnetic drag on a full sphere. This is why it's called global circulation. And this allows to study interaction between outer and deeper circulation pattern, and also to study the effect of the circulation on the spectroscopic signature, like those which can be detected by HST, Spitzer, and GWST and ELT. So here I would like to point recent developments that we are doing in Exeter, at the University of Exeter, and where we're using what is called the unified model of the Met Office, of the British Met Office, which is actually, we are using the tool which is used to predict British weather and we adapted it to exoplanets. The main advantage of this tool is that actually it solves the full hydrodynamical equations compared to almost all other global circulations models which have been applied to exoplanets, where usually those models assume hydrostatic equilibrium. We do not assume, we have the full hydro equations. They assume some kind of shallow atmosphere where you neglect the thickness of your atmosphere compared to the radius of the planet. And they usually assume as well constant gravity. We don't assume all this, and this means that this tool actually is very well adapted to study the interaction between deep circulation and the high atmospheric circulation, which is required if you want to understand inflation of planets. Actually, you may ask me, why do you need such a sophisticated tool to predict British weather? Because, as you know, it's always very sunny. And I will not answer this question. I think the most important question is whether we need this sophistication for exoplanets. And now it's important to know that global circulation models have constraints from observations. And one of the very nice constraints, as Kevin Heng has been highlighted yesterday and as Ray J have shown us, comes from actually orbital phase curves. And for example, this has been already mentioned, orbital phase curves suggest that for one of the transiting planet, AG209, you have this hot pulse, which is shifted eastward of the substellar point. This process actually has been, in agreement, has been predicted by various global circulation models like Schumann, Manu, etc. And I just show here, well, it's just what you see here is that you have these super rotating jets which go from the west to the east, and this is the type of what those simulations predict in total agreement with observations. But actually, from our preliminary results, we find that the property of this jet is very sensitive to the type of assumptions you are doing, whether, for example, you assume hydrostatic equilibrium or not, whether you assume shallow water or not. And we also find that the property of the jet is very sensitive to the gravity of the planet. And we even find that for low gravity of the planet, the jet may reverse. Therefore, in some cases, we may predict a hotspot which would actually be westward. So we are still trying to understand what's going on there. This is absolutely preliminary. It may be wrong. As you know, global circulation, well, simulations are simulations. So now we are trying to understand this. This is very interesting, but I think it's absolutely key to combine transit and radial velocity data, which will give us, for example, the planet's gravity and also phase curve to understand this hotspot shift. And when I mean phase curve, it would be with a wide range of wavelength. I know I'm asking a lot, but this is your job, you observers, yeah. So I'm going to finish here. And I think in terms of modeling and theory of exoplanet, first of all, it's very important to know that now there is a huge effort which is made to develop ab initio equation of state. We'll have very soon very new accurate equation of state, and they are not only laboratory experiments which are helping this, and for example, we have the laser megajoule in France, which actually can test directly matter at pressure, which are characteristic of Jupiter and Saturn. And also, we have first principle methods which are being developed. So new generation of planetary models are coming due to those efforts with equation of state and improvement. Other point I would like to highlight is this question of whether planets are fully adiabatic or not. And here, numerical simulations, I think, are the only way to help and to see whether you can indeed have this process of double diffusive layer, and whether, if you form layers, they can actually survive during billion years of evolution. But what is interesting also is that there is a potential observational signature for young planets who would have double diffusive convection, because they should be very faint at young age, typically a few million years. And final point is that the development of sophisticated dynamical atmospheric models is not necessarily to predict weather on exoplanets, we don't care about that, it's to try to understand fundamental fluid dynamics and MHD process on those planets, which may help eventually to solve one big puzzle: why are so many hot Jupiters inflated? And also may help understanding and interpreting observational signatures. And the last point is that we need orbital phase curves, and we also need some kind of measurement of wind velocity. And Snell and al. Has recently shown with high resolution spectroscopic observations that it may be possible. So future looks quite good. Thank you very much.
So questions to Isabelle?
Comment on CoRoT20. I've just checked this. I did a solution of the light curve myself back in 2012. I came out with a radius of 1.16 versus 0.84, and with a much larger error bar. So I suggest that we don't really know the radius of this planet yet. So, more data needed.
Okay.
What do you think happens to convection at the interface between normal and metallic state of the plasma?
So between the
gases and the
molecular,
and the metallic.
The molecular and hydrogen and the metallic hydrogen? Is this, or is this your question? What happens? It depends.
To convection.
Yeah. It actually depends whether you have eventually this phase transition, which would mean a discontinuity in density and discontinuity in entropy. And therefore, if you have a discontinuity in entropy, convection does not like that. So you will have actually those two different layers. So it all depends actually on this, on whether you may have a first order transition or not. If there is no first order transition, then what will happen is that your convection will just go on. Actually, dissociation of molecular hydrogen is a very fast process, so it would not somehow prevent your convection. So it very depends on whether you have the first order transition or not.
Yeah, I have a question about this, your comment about this Leconte-Chabelier model. They used J2 and just J2 to infer the global metallicity of Saturn and Jupiter. I think that's what you said, right? They infer the global metallicity of
they
Saturn
infer the
and
global
Jupiter
metallicity.
just using J2. Is that right?
And G2 and G4, the gravitational moment, both.
Okay. And then what you said is that if you have measurement of higher order J's, and this can be immediately tested.
You can test this idea, absolutely, yeah. It's only G2 and G4 because this is where we have the main, obviously the best measurements so far. And, but it's true with Juno, for example, this can be again tested.
So the difference can be very large, can be immediately very large, basically, once you measure J6. Is that right? I mean, basically.
Yeah.
Okay. That's very interesting. I didn't.
Very last question, all right.
Very nice talk, Isabelle. Can you comment a little bit from your kind of ongoing simulations about the vertical extent of the jet? Like where in the atmosphere is it most prominent? And you know, what layers should we be sort of targeting?
This is typically about, let's say, 0.2 megabar, something like that. So this actually can be tested by, the thermal emission at 4.5 micron, for example. But so this is actually, I would call the photosphere, if you want, if there were a photosphere on this type of planets. So this is about the 0.2 megabar, between 0.2 megabar and 1 megabar, something like that. 1 millibar. Yeah. Mm-hmm. After it all depends. So yeah, I haven't looked really very much at that because first we really want to understand. So I would not say anything. That could be wrong.
Okay, thank you again, Isabelle. We have to move to our next speaker.